All right, welcome to the Explainer. Today, we're diving into a paper with a claim that just sounds impossible. We're talking about teaching a giant AI how to reason using an update so small it's almost nothing.
So let's just start with this number because it's really the whole story. 13. Not 13 million, not even 13,000. Just 13. That's it. That is the total number of tiny little knobs or parameters that a huge AI model had to tweak to learn how to do complex math.
And if you think that's wild, get this. The size of that lesson is just 26 bytes. I mean, that's literally smaller than the file name you'd give the document. It's so small you'd think it's a mistake, a typo. But as we're about to find out, this ridiculously tiny key unlocks a massive new ability inside an AI's brain.
So that's the big question, right? How on earth is this possible? How can you teach an AI so much with basically no information at all? This goes against everything we thought we knew about training these things. Let's dig in and figure it out.
Okay, let's get into the heart of it. We're calling this the 26-byte secret, and it's not just some weird, quirky finding. This could totally change the game for how we build and train AI from here on out. You know, the funny thing is, the researchers didn't just accidentally find this. They were actively pushing the limits. They started with a method called LoRA, which is already famous for being super efficient. They took the absolute smallest version of it, and then they asked a crazy question. What if we make it even smaller? Like, ridiculously small. They were basically challenging the status quo to see if it would break.
Now, to really get why this tiny update is such a big deal, you have to understand the scale of the AI we're talking about. This isn't your smartphone's little assistant. We're talking about an absolute behemoth. 8 billion. That's how many parameters are in the model they used, which is called QN 2.5. Think of each parameter as a single dial in this giant, complex brain. Trying to teach it something new by adjusting all of them? Yeah, that's like trying to rewire a person's brain one neuron at a time. It's just not practical. So when you've got a model this massive, you usually have two choices. You can do what's called full fine-tuning, which is trying to adjust all 8 billion of those dials. It works, but it's crazy expensive and takes forever. Or you can use the clever shortcut, LoRA. What LoRA does is it freezes the main brain and just slaps on this small new adapter that you train instead. It's way more efficient. But the researchers, they looked at this shortcut and thought, can we make this shortcut even shorter? And their answer to that question was a new method they came up with called, you guessed it, TinyLoRA. Now, TinyLoRA isn't just LoRA on a diet. It's a complete rethink of the whole idea. It's about shrinking that training adapter down to a size that's just mind-bogglingly small. We're talking about going from thousands of parameters to maybe just a few. Or, get this, potentially just one. And this chart really puts it in perspective. We were all so impressed when conventional LoRA came out, right? Training thousands of parameters instead of billions felt like magic. Well, TinyLoRA just blows that completely out of the water. It's not just an improvement, it's a whole different league of efficiency. Okay, so you're probably thinking, sure, it's small, but it can actually work well, right? Well, that's the craziest part. It works incredibly well. The results are just stunning. By using TinyLoRA to train only 13 parameters, this 8 billion parameter model hit 91% accuracy on a set of grade school math problems. It didn't just learn a party trick, it actually learned how to reason. So this brings us back to the big how. How is this even possible? The TinyLoRA method is one piece of the puzzle, for sure. But here's the twist. That tiny little key only unlocks the door if you turn it in a very specific way. It turns out the secret wasn't just what they taught the AI, but how they taught it. And that special how is something called reinforcement learning, or RL. The best way to think about it is like teaching a dog to fetch. You don't give it a manual, right? You reward it when it gets closer to the goal. It's all trial and error. For the AI, it got rewarded for every correct step it took in solving a problem. It wasn't memorizing answers, it was learning the process of finding them. And this right here, this is the final piece of evidence that just seals the deal. The researchers tried another way, a more traditional textbook method, called Supervised Fine-Tuning. And the difference is, well, you can see it. It's night and day. To get the same level of performance, the textbook method needed hundreds, even 1,000 times more parameters. So reinforcement learning wasn't just a little bit better. It was the secret sauce. So let's recap. A tiny, tiny update combined with a very specific way of teaching creates a massive leap in ability. The big question now is, why does this matter so much? Why is this microscopic tweak such a huge deal for the future of AI? Well, the implications are pretty huge. For one, this kind of efficiency means that customizing these powerful AI models could become super cheap and fast. That's a game changer for accessibility. It's not just for big tech companies anymore. But here's the idea that really gets me excited. What if these abilities like reasoning were already inside the model, just lying dormant? What if the training didn't create the skill, but just unlocked it? And finally, it's a massive win for reinforcement learning, proving it's an incredibly powerful way to teach complex skills. And that really leaves us with this one mind-bending question to chew on. If mathematical reasoning, a pretty complex skill, can be switched on with a key that's only 26 bytes, what else is hiding in there? What other giant abilities are just sitting inside these models, dormant, waiting for someone to find the right tiny little key to wake them up?